So what we will do next, the first thing I would do here, I would like to have a short glimpse to the hardware, only to the 1 and 2D. I jump over all the other stuff. If you are interested, I really suggest to have a look to the PDFs of these slides, and if you have special questions, simply let me know. We can discuss this. And of course, next I would like to have a look to light and lens. I mentioned it before. Light and lens, for many, if you have not so much experience with machine vision, light and lens looks not so important, or seems not so important for most of the people. But of course, if you have if you wear glasses, you know lens is important. But anyway, most people don't recognize that light is as important, and especially for 1 and 2D, because for 1 and 2D, you can simply buy a camera and nobody tells you why your machine vision solution is more a dicing game than a stable solution. And in, let's say, 50% of all cases, it's the light and the lens. So that's why I would like to have a look about 5 to 10 minutes to the light and lens, so because this makes it easier. And based on this, we will have a look to the iVision instruction set, how to work with, of course, 1 and 2D images, and how to make it with iVision. So I will show you some examples for 1 and 2D with the iVision software, with some real images, and finally we will see some of the ready-made examples which you can also download and have a look by yourself. So all these examples are ready for download, so that you can see how to do counter matching measure and many more, which we'll see later. Of course, I've forgotten here the color. We will also have a look to color, especially maybe someone has time tomorrow and will attend the color session. That's why I don't have a too deep look to the color today, because tomorrow it's all about color. But color belongs to 1 and 2D. That's why we have a short glimpse to it. Yes, and of course also some words about help and support. We know from our experience, help and support is really important. If you are not so experienced, it will give you a real fast entry to machine vision. So the first thing is, because we will see it in many details later, the iVision today, and especially the user interface for the developer. This is only a glance to it, and as you can see, because it's the oldest part, let's say since I think nearly the 80s of the last century, it's 1 and 2D imaging. Even with these, let's say, very basic cameras at that time, they were mostly based on normal TV cameras. Everything starts at that time, and so that's why most of the algorithms are available for 1 and 2D image processing. And of course, because things changing, if you have a look to our 3D stuff, you will see, okay, 3D stuff is growing fast, because this is an option for many tasks where it's easier to make a solution. So we had already some 3D webinars, but we will also hold some additional ones. And if you're interested, also webinars are available to download or have a live look to it. Simply feel free to go to our YouTube channel. Finally, if we if we discuss about 1 and 2D, also the question is always, do we need filters? The question is, what kind of filters? Do we need electronic filters like here? So if you open up the filter section, I didn't open up everything, you will see there are a lot of filters, but as you will see it in a few seconds, before you use electronic filters, you should use light and lens and filters. That means physical filters before you use electronic filters. Why I discuss it in a few minutes. So of course there are object tools, counting and matching, and color tools, edge detections. These are all 1 and 2D tools for evaluation. Also, of course, we have a lot of code reading tools for all these standard codes and stuff of illumination and image information. There are a lot more tools to work on 2D image, 1 and 2D images, gray and color. And yes, so let's have a look to the right light filter and lens. We have this ray of light presentation, and of course you can get this also as a PDF, or if you need some more background information, I would suggest that you will take some time and attend the webinar about light and lens. So what means light and lens? At the end, of course, we do, in this case, 2D image processing. And so many people speak at the first thing, what camera, what processing unit, and of course, what kind of software. But the main important thing is on the left side, the light, whatever light it is, the lens, and the lens with the filter, and finally then the camera. It could be any of the standard cameras. We have a look in a few minutes to all these different hardware options and which camera is the right one. But as you can see, the camera is more not on this 50% light, lens, and filter. It's more at the 50% of sensor hardware and software. To do what we really want to do at the end, we want to make a stable image analysis on, for example, a conveyor belt. And of course, here sometimes the question is, do I need a 2D camera or 1D camera? In many cases, or a 2D camera is, or let's say in most cases, a 2D camera is pretty good to make the solution. In some cases, especially for endless material, like woven stuff, line scan camera is much better. Especially there are a lot of advantages like no reflection. Of course it's no reflection because it's difficult to hit the sensor from different positions based on the how the sensor is built. It's only a few micrometers width, and it's difficult to get a reflection on this exactly position. But also you get nearly you get an image which is nearly endless, or if you throw away the incoming lines after a while, you have an endless image. But you have images with real large sizes, much larger than even if you buy a 40 megapixel area scan camera, and you get it with a much higher resolution and a much higher speed at the end. So the discussion, which should I use a line scan camera or area scan camera, is a long discussion, but and it needs some experience. In many cases, people use a 2D camera only for the reason because they get an image and they can see it, because the line scan camera needs some more preparation for the image capturing. So, but first, one of the golden things is wrong lengthened light, and this is the truth which you have always in your back brain. Wrong lengthened light means also the filter means bad machine vision, and good lens, filter, and light means good machine vision. At the end, it means generating contrast. And in most cases, if the machine vision is not stable, it's not the question about the software. In most cases, it's the question about exactly this position, lens and light. And of course, all this lens and light, it means at the end generating contrast. And if you have a good contrast, you can make a good algorithm which is stable. If you have a bad contrast, you can program like hell, or you can think about all the algorithms you can do. You don't have good results because good contrast means a good signal, and a good signal in this case means a good image. If you have a high-end oscilloscope, of course, and you have a horrible signal, maybe you can see something, but not stable. But if you can improve the signal with your probe at the front of the oscilloscope, even a bad one can work. And exactly, it's the same for machine vision. Most people simply forget it, and that's why we always recommend and try to bring it in the forehead. Light and lens is really important. What is light? So for machine vision, light is everything. Everything which can be detected with a kind of sensor. Most people who discuss about machine vision, they discuss only about this very small area here. This means the visible light, but the interesting thing is for some solutions, the non-visible light is the better light because it exactly shows you what you want to do. I give you also some examples later, but a simple thing is if you want to see if a gluing is working, hot gluing, if you want to glue something with a hot glue, which is done in many cases in the factory automation, you can use any kind of visible light camera, and in most cases you don't see anything. If you use a camera which is active in the infrared wavelengths, you get immediately the temperature of the glue. First of all, you see the glue and you get an idea of the temperature, even if it's behind, let's say, some paper or carton walls. And you simply can measure this and you can determine, yes, there is glue, the glue has the right temperature, so it works. You don't see anything with the normal camera. So that's why the first thing is what I want to do and what is the right wavelengths means what is the right camera at the end. Of course, the majority of all manufactured cameras work in the visible spectrum of the light. This means in this spectrum here. All the other cameras normally are much more expensive, and but it's simply, you know, it doesn't help you if you have a cheap camera and you cannot solve your task. For example, if you want to look into a tire, if the steel inlay is okay, you can use any camera, you don't see it. If you use the X-ray camera, you can simply see the inner part, like a X-raying of whatever. So, but there are a lot of other applications where, for example, a thermal camera might be better. So, but this depends on the task at the end. So, of course, because I think roughly 90%, 85% of the machine vision solutions today work in the visible area. We have a look to two parts. One is the color and one is the other one is the gray. So the gray is the mainstream also because it's one of the oldest one, and especially based on everything, the amount of data which is generated by the sensor, it's much smaller than for color, because to transport color information, full resolution color information, you need at the end 3 times the data of a gray image. But on the other side, there are some other problems. And of course, nowadays it's much easier because we have these also high power LED lights. But for the very beginning, and that's why also many people don't want to use color at all also today. And it's still valid based on surrounding influences like sunlight or whatever. Color is very sensitive. That means, of course, our eye is always recalibrating our brain, or is always recalibrating the eyes based on the surroundings, so that we see always red as red. But the camera doesn't see red as red. Of course, at the end, you need it's called white balancing, and you have to do it actively. The camera supports it, but you have to initiate it, and you don't know when. You cannot do it every second. It takes some time to do the white balancing, so you have to do it maybe once or every few hours to be sure that the camera sees the right color with the right color based on the current illumination. At the very beginning days, or let's say not so long ago, I would say roughly 10 years ago, before we had the real high power white LEDs, if you made a solution for a color 2D color application, you needed powerful light, powerful white light, and some people use these, let's say, normal light bulbs. Some use the natrium high pressure lamps and so on. And the problem for the human eye, and that's why most people don't understood it, why it's not working for a long time, these lights change the light temperature. And the camera sees not only the color of the part, it sees the color of the part based on the light temperature of the light. So nowadays we have these stable LED lights. At that time, first of all, the normal bulbs with the normal light bulbs, which we know for a long time, they change their color temperature based on the time and on the aging. So if you bought a light, the first 3,000 hours, or let's say 2,000 hours, you had, first of all, at the beginning, you have a heating up period where the light color changes. Then you have a stable period, and then the light color decreases in any direction. For the human eye, there is no difference because from the automatic recalibration. For the camera, there is always a difference, even for the newest cameras, because of the recalibration, the white balancing. And that's why I have it today also. Even if you have this nice high quality, high power LED white light, which doesn't change the light normally, the light temperature, sometimes it happens that maybe during the time you get some sunlight inside, and it hits the area where the camera looks, and then the white color is moving. And that means at the end, for your solution, of course, you get false, you get wrong decisions from your software, because red is no longer red, or blue is no longer blue, the blue which you trained, because the color of the light changed, but not your object. You can test this. It's really amazing, and only if you saw it, you will see the effect of these different light colors. This is one of the reasons why most of the machine vision is done in gray, with gray cameras today, not about the amount of the bigger amount of color images. It's more the stability at the end. And of course, also for gray images, it's important to have a stable light, but they are not influenced so hardly from the color change of the light. So that's why before you start making a solution and think about the solution, you should think first of all, what is the task, what should be stable, and then sometimes a gray application, a gray camera with a fitting colored LED light is much more stable than a color camera with a white LED light. This needs some experience, and you have to take it in mind. Of course, I could speak about this for hours, but this is only a short intro that you have it in your mind. What I meant with the right LED light for a gray camera shows this example very well. So you can eliminate with the fitting LED light, for example, the apple out of the image. So if you are disturbed by the apple, you can do this. Keep it in mind, and if you have this kind of questions, you're welcome to call us, and we can give you some ideas. Of course, there are not so many options to illuminate it, so you can either have an absorption, a reflection, a transmission, or emission. Emission is either if it's a light by itself, if it's in the viewable, in the visible area, and interestingly, this emission is mostly really interesting for thermal imaging, because in this wavelengths, many of the targets do emit heat, which is very easy to detect. You cannot, for most of the people, it's difficult to understand. You need a thermal camera and look to it and to understand that it's easier to use for some cases, this kind of camera. The other is, as we saw here, we have this different reflection, transmission, and so on. If you have exactly the same part, so we can do based on different light effects, we can optimize the way how to do the evaluation. So for example, if you want to simply count these two white parts, these are condensators, maybe independently on the background, maybe this light is much better. You see, this is only, the difference is only the light source. And the light source means the angle with how the light hits the surface of the target. And this makes it much easier and totally independent if you select the right one. So now I do only a quick step over this very long thing. So I think you can see the right solution is the right for it's much easier to solve it like the left one. And here also, if you want to inspect this, let's say, plastic part, the right one is easier to do. And especially, of course, this might be interesting, and the tools are in the software to give you an idea why is it better to use this kind of light and not this one. As a human, you can see, okay, the shape is okay. But for a machine vision solution, the right one is much better. And why? If you have a look to it, as the human eye generates the shape, but if you look to the real data in the image memory, we see here, of course, it looks like it's not perfect, but of course it's perfect. If you have a look at this position in this image and this image, it's the same part at the same position. We simply can detect the outline of the part very well. So only one example for it. Or if you have to inspect these kind of connectors, of course, this is a pin inspection. At the very beginning, you have to mostly to count the pins and see if the pins are at the right position. Mostly you want to know the height also. Nowadays you would use a 3D solution, but you can do it with the right light also in 2D. Because at the end 3D is not so old, and it makes it much easier. And if you want to read code, of course you need contrast and the right light. Or here, even as a human, you cannot read it. Or if you have to do this kind of read application, whatever you do, you have to improve the light. These are only some examples. I think if you see it, you know, okay, I have to do something with the light. Here is some an example for, let's say, a special lighting with a red laser. So you can do it also with as a normal light. But if you saw our 3D presentation, you know, a lot of sensors make based on this real measurements with a point cloud. Or what I told you before is what is the right wavelength for the solution. And so in some cases, for example, if you have this kind of fruit, you have any kind which is sealed, and you have to check the seal with a normal color camera or even a gray camera, you cannot see if the seal here is perfect. But if you take, if you use a thermal camera, you can see here immediately the seal, and if the seal is good. So also light is also maybe a wavelength which you don't think about. And if you have this kind of application, you will never be happy if you use a normal camera. Of course, if you want to read the print on the part, then you need a color camera, and maybe a gray or color camera, but in all other cases, it makes no sense. So maybe another thing is, if you want to measure in 2D, you have always to think about the lens. This is another point many people don't think about, especially because for the human eye, it's not really necessary. Our brain does a lot of pre-processing, and we see it, but we don't realize it, that we automatically do the right alignment to see what we want to see. Here on the right side, I have this connector. You see a lot of solder pads on top. And if you look from this, of course, we can see on the top, maybe they are on the same line, but we have to see if they are really on the same line. We would do it the same way if you do it with the eye. We put it in front of our eye, and we look exactly to this one, and then we move it, or move our head a little bit, look to the next, and so we go through all the right rows, and we will always see, like in the center, how it looks like. If you have a machine vision solution, mostly you cannot move. Of course, you can move the part always in the center of the lens, but in most cases, based on the production speed, you can't do it. And in that case, there is no way, if you use a normal endocentric lens, this is what as an endocentric lens is also what your glasses are, or how your eye works, you will not be happy. Or if, for example, if you have any deep part, like this Lego part, but it's also, I show you another image, some holes which are drilled or whatever, it's difficult to measure the distance here. Of course, as a human, you can see, okay, here is I have to measure from here to here. If you look from the top, as a human, you can say, okay, I have to measure from here to here, but of course, we cannot measure with our eye. So at the end, you have to think, how can we see why we don't measure here on the bottom side and not on the top? Difficult. That means if you have this kind of application, so parts with the depth, then you have to think about a different lens, and therefore the endocentric lens are the right ones. And if you have a look to the same parts as before, I think immediately you will see the difference. So here we have in this the whole area field of view, without moving the part, we see all these solder points. And also here for this Lego part, we see here, this is the edge and this is the edge, because we don't see in the depths. It's a parallel rays of the telecentric lens. So if you have to do some measurements with depth parts, normally there is no option to use endocentric lens. You need always a telecentric lens. Here the same for between endocentric and telecentric. The same part on the top, you see the endocentric solution. On the bottom, you see the telecentric lens. Here you see exactly what you see also with your eye. If the same person is closer to you, it's bigger, and it's farther away, it's smaller, because we take only the parallel rays. It's exactly the same height, so you don't have to think or correct whatever. If you can, of course, here you could calibrate. In this case, you could calibrate the field of view on the back and on the front, and you can measure it anyway. But if you cannot calibrate, or you don't know where it is, at the end, it's much easier to simply use a telecentric lens. And finally, there are also some special lenses, which maybe today are not so important. The camera is going to be very cheap. Maybe today, if you only want to see if the prints are good, you could use this hypercentric lens to get an idea about the sites which you don't see. If you have to measure it or so, you need more cameras. But at the time when it was active, this was the right thing. But in another example, which is really important, if you build a solution where the size is not, where the machine is fixed, and you have to integrate a camera solution, you can calculate an endocentric lens always for a special distance, or you can set it to a distance where it is sharp. That means at the end, if you could not generate the distance, so you have a sharp or unsharp part. Here we have two. One is this milk bottle. On the other side, you see this PLC. And of course, if you have no option, there is it's called Scheimpflug. It was a photographer in the beginning of last century. He wanted to photograph large buildings, and he thought about it, and then he got the idea that if he tilt the lens, then he could manage that even an endocentric lens generates you a sharp image over the complete field of view. As you can see here, here it's unsharp and here it's unsharp, but here on the Scheimpflug lens, you see it's completely sharp and you can evaluate it. So no electronic filter will give you back this information or this information. Electronic filters can only improve signals which they have, but here the signal is totally crap, and the filters wouldn't help. What helps is the right lens. And maybe a short view, I also mentioned it, about filters. Filter is another option how to improve images. So if you have to inspect, for example, a kind of image, or on a bottle something, if you use the right filter, you can eliminate the lighting effect, the light effect, or you can eliminate some the effect of reflection from some foils. Or here you can see these shining areas, you can eliminate them, and much more. Or you can improve the contrast. The very beginning was, of course, a human eye can see this is the inlay, the metal inlay, but it's difficult to really get a good contrast to have it stable. If you use this filter, you see the plastic is white and the metal part dark, and that works. Or you do some band passing. This is a a good thing, especially if you are in the factory automation with a high-speed inspection, and maybe you generate a flash for every produced unit with, let's say, 10 or 20 parts per second, or 30. Then you have 30 flashes to get an optimal illuminated image. And if you have some humans around it, that means these people are not very happy after a while to get all these flashlights in their eyes, which means at the end they cannot work after a while. So in this case, you could use a different wavelength for the light. So we don't. The camera is active in a white white area. If you have a look to this spectrum, and if we go, let's say, into this ultraviolet here, the human eye doesn't see anything. It's like no light. And if you use a filter, which works also in this one, so the camera can see this light. So if you, as a human, if you look to this area, you see nothing. The camera sees it's illuminated. And of course, we have this normal light for the humans. So we get front light for which disturbs here, because we see the camera has a wide spectrum. And in this case, we use a filter which eliminates the daylight. So that wherever daylight is, it's black. And of course, the frequency of this light goes through. So for the camera, it looks dark and bright. And of course, it's much easier to detect. Of course, you can detect this here, but this is much more stable, especially if you have to measure very exact. The higher the contrast, the better, and the more stable is the measurement. So that's why all the stable machine vision solutions try to improve the contrast as good as possible. And mostly the nearly binarized image is the most stable one, because effectively the algorithm has not a lot of decision to see where the edge is. So here he could put the edge 1 pixel deeper or not so deep. And that means at the end you measure different values. And if you have to measure it in micrometers, you would say each pixel has, let's say, a micrometer or whatever, depending on the calibration. So it matters if you have a good light. This is what we really recommend before you think starting doing the evaluation with the software. Do the improvement either with the light or with a combination of light and filter and lens. In this case, it's no question. I think we don't see something, the camera don't see something. These are always camera images. But if you use a fitting filter, we can eliminate the normal light, and we get the rest. What is left over is only in this case, the DMC code, and it can be read here. No contrast, here contrast, which simply means you can read it. And there are a lot of examples. I think you can have a look to it when you download it, or if you attend the webinar about lens and light, you will get some more information. One thing for the end, we discussed about color image evaluation. Of course, you can use a color camera with the problems I mentioned to detect are these red or blue. In many cases, you know exactly what you are producing at the machine. But you can also do it based on a filter. In this case, you see these color separation filters. So everything what is red is bright. And in this case, you can see how many bright parts are here and black parts are wrong, or vice versa. If you use a filter which passes the blue, then the blue is dark, the red is dark, and the blue is bright. So this is another option. This is the main thing what I want to discuss about filters. I know, and this is really important for 1 and 2D image processing. So keep in mind, have a look at it. And if you need some more information about filters, simply feel free and contact us. We have some experts here which can help you. So of course, these were our short excursion to filter. One of the next things would be the different data streams. Data streams means, in our naming convention, images, because what is an image? An image is at the end a data stream, either, and depending on how it's arranged, it's a 1D data stream. If you collect the 1D data stream, you get also an area. Or you have a 2D data stream. That means you get from the sensor X and Y data all the time in the resolution of the selected sensor. And the iVision software, of course, can capture them independently if it's in a gray, a color, a thermal image, or some of the others like 3D or hyperspectral. So what kind of cameras are there in the market, and how can they be connected to the, especially to the iVision software, or what is the right camera for what? It's the right camera for what? It's a discussion of the part, of course, but first of all, we can have a look to the vision sensors or the smart cameras, because this is a special category, means the integration of the processing hardware to the sensor in one housing. And the other thing are any kind of separation between the processing unit and the cameras. The cameras are connected then based on either nowadays USB 3 GigE. The latest thing in the world is the MIPI interface. Everybody knows it, maybe or not. This is the interface which is used in all the mobile phones to transfer the camera images to the main memory. And as long as the distance is not so big, the MIPI interface is rather good. And of course, for high-speed image acquisition, there is Camera Link and CoaXPress. Camera Link is the old standard, where it's way back from the, let's say, mid-90s to the early 2000s. And based on the restrictions of the cable, thick cable, expensive cable, CoaXPress was invented by the machine vision industry, which allows to transfer large amounts of image data over, I think if you see it in the name, over coax cables. This means you know them nowadays mostly from satellite the satellite cable, which are in your home. Of course, finally, there are still analog cameras out there. So the beginning was the analog standard. Analog means you have a camera which transfers the image data where each pixel or each pixel is represented as an analog value in a signal. I think since let's say the early 2000s, the analog interface are nearly vanished. Today, there's only you find the analog interface mostly in surveillance applications, but there are still some machine vision solutions out there which use these analog cables. So before we go one ahead, I take a short excursion and I go fast through it to the hardware which is supported by iVision, which also gives you an access to the 1 and 2D cameras. Of course, here we have some 3D and other camera stuff, but I don't want to discuss this today. You can see this if you download it or if you attend one of the other webinars. So let's start with the smart cameras and then have a look to the embedded systems and also the PC systems. These are nearly the same. And finally, to have a short overview about the cameras with the different interfaces. I don't mention all the manufacturers only for the smart cameras because there are not so many. I simply go through these ones. So if you have, this is, let's say, The first are these x86 based 2D cameras. That means there is an, let's say, Intel x86 compatible, could also be an AMD, but most are right now Intel CPU inside. And as you can see here, there is a C-mount connector. That means there's also a sensor inside of it. You have some PLC I/O, and depending on the manufacturer, you have also gigabit Ethernet and sometimes a video connection. So you can program it like a PC. Here, the difference is you do not have to connect the camera over an interface because the camera is integrated. This belongs also to these other cameras. It's always a PC with a sensor with an integrated PC, or a PC with an integrated sensor. So which one is the best? I don't know. One have to think about it. Mostly it's price-wise or heat-wise. If heat is a question, normally systems based on ARM are state-of-the-art, because ARM CPUs are much better in performance per watt. We know this from our mobile phones. They could also operate so long because the CPU doesn't heat up even for a high-speed processing. So therefore, you see these other smart cameras. That means it's a sensor, and there is a ARM, mostly an ARM CPU with 1 or 2 cores inside. And as we see here, these are all area scan sensors, means 2D sensors with different resolution. Of course, the limitation of these smart cameras is mostly how many sensors does the manufacturer integrate, because you are dependent what the manufacturer thinks is the right resolution or what resolutions they want to integrate. This is the only restriction. Mostly you can select by size or whatever. The software runs inside of the camera, and you can do the same like you do it on a PC, of course, with the CPU speed. You get here in the average 1 gigahertz with 1 or 2 cores, of course, now. Meanwhile, also 1.6 gigahertz. It's not, let's say, like a PC, but for most application, even 1 gigahertz is much enough. It's much more than enough for industrial application. If you have a normal production line with, let's say, 5 parts per second, then 1 gigahertz is fast enough in most cases. There are always cases which are should be faster. And as I told you, sometimes you don't find hardware, and then it's needed to make a solution. In this case, we had some customers for smart line scan cameras, and we didn't found one in the market. Of course, you get only some more or less replacements, like read only one line out of the CMOS sensor, or of these other area scan cameras. Finally, it wouldn't work based on the resolution. And that's why we said, okay, let's build this kind of camera. And so the Jupiter series is one of our own hardware. We didn't build these area scan sensors because you saw there are so many manufacturers who built these area scan sensors. It makes no sense for us to make also one more area scan camera. And as you can see, you get a 4068 pixel per line. And of course, you can see it maybe here in relation to the other. You see here the normal. You cannot see the sensor inside, but maybe here. No, here we see, here's an area scan sensor, and of course we don't have an area scan sensor. This is a line scan sensor exactly behind this slit, and you can run it on endless material, woven or non-woven, and do the evaluation. One advantage is right now with the latest upgrade, you have the Coral chip inside, which enables us also to do deep learning on the fly with full speed. So we have some special networks now which we can run also inside of this camera. This is also one of the advantages of this design. We have this neural processor inside which enables us to make fast neural solutions. And because of this neural sensor, we improved the complete hardware. So you can get it now with the latest ultra scale, which is double in the core, in the CPU core. It means 1.6 gigahertz. And we also added the area scan sensor to have this smart camera with the Coral neural network speed improvement to enable our customers to have deep learning in embedded cameras. So all the others, and for the moment I don't see any other smart cameras. So here this is another area scan smart camera. You see here the area chip slightly. These are simply CPUs, and of course you can run neural networks on CPUs, but at the end if you want to run it fast, let's say with 60 frames per second or so, you cannot do it on these standard CPUs. And there you need a special hardware, and we didn't found it. Once again, it made sense to make it. This is another smart camera. And finally, as I told you, you have these standard camera solutions, and maybe you don't need a PC, you need more small embedded system, maybe with less heat dissipation or with a small footprint or whatever. So there are a lot of options, all based on ARM CPUs, where you can connect either a MIPI or a USB 3 or GigE camera. Here you see, I think it's one of the most popular hardware units in this area, the Raspberry Pi 4. Or 3 or whatever, but also most of the others do have this MIPI interface because these CPUs do have the interface, and the manufacturers added it. So you can simply use one of the MIPI cameras, connect it to the board, and capture images from here. Of course, once again, it would be nice to have a MIPI line scan camera. There is no one because unfortunately the handy manufacturers didn't saw any reason to support or build in a line scan camera, and I don't see a reason why they should do it. So if you want to use with these embedded systems a line scan camera, you have to use one with standard interfaces like USB 3 or GigE, which let's say makes things only a little bit bigger because you have to connect it to these different connectors. You see these GigE, USB 3 or GigE connectors also on all of these other of these units. So these are simply different of these units. Of course, we support these NVIDIA, Xavier, or all the others, which you can also run then really fast deep learning. Of course, the size is not so small, so you could, yes, it depends on the heat dissipation field. Maybe if you use if you do a 2D application or 1D application, if you use Tegra or a normal PC. But in this case, you have, of course, here it's also supported the MIPI interface if you have an area scan sensor. But in many cases, you can use either one of the standard connectors of these embedded systems. Of course, you have also small PC boxes, which means at the end, there's a x86 compatible CPU inside and a lot of connectors. All these connectors will result in one of these standard 2D or 1D cameras, of course. Maybe the advantage is depending on the manufacturer. If it's PoE, means power over Ethernet. If you use an Ethernet camera, the advantage of Ethernet today is the advantage of Ethernet related to USB 3 is, of course, the power consumption, or the power, it's not the power consumption, is the length of the connection line. So if you have USB 3, it's limited, let's say, to 5 meters or so, let's say 3. And if you have GigE, you have the normal cable length for GigE, and you can use any kind of repeater to make it even longer. So there is no problem to have 25 or 100 meter for GigE camera to connect to a PC. For USB, these PCs have to be somewhat close, but in most cases that doesn't matter. So you are nearly free to use any kind of these PCs. Of course, these very embedded systems, you can use all of these standard PCs with the standard plug-in boards. From price-wise, if you do 1 and 2D image processing in the normal speed area, normal speed, I would say up to 40 parts per second, you can use simply USB 3 or GigE nowadays. Of course, you can run it also depending on the resolution faster. And so there's no need to, in most cases, to plug in a special capture board. But of course, there are some applications which needs faster access, or they have more cameras and so on. Then, of course, you need, beside of the GigE and USB 3, I think USB 2 is outdated, as well as FireWire. You should only use GigE and USB. In our opinion, if it's much faster, then you could use either Camera Link or CoaXPress. If you build a new system, of course, CoaXPress is the right one, because Camera Link is more expensive and is going to go out of the market in the near future. If you go to these 2 additional interfaces like Camera Link, CoaXPress, also, in the meantime, if you want to use FireWire, you need additional plug-in boards, analog interfaces, and anyway. And there you have to select between one of the manufacturers. All of these board manufacturers, if you want to use this, they support all kind of interfaces. Of course, they support always Camera Link and CoaXPress. That's the main target for these boards. Because the standard interfaces you can buy for much lower price are fast enough to support the speed of the GigE or USB 3 cameras. In some rare cases, this plug-in board is anyway makes sense, but for these rare cases, one have to think about it if the additional price makes it is valuable for that. So these are simply different manufacturers who build this kind of boards, which allows you to connect these CoaXPress, Camera Link, and some other interfaces. So this is all about the standard interfaces and the additional interfaces. I mentioned the USB 3 GigE. What's interesting is right now in the 2D area, I think the line scan camera will follow up very, very soon. But the mainstream is anyway 2D gray and color cameras. 10 GigE is upcoming. So what does it mean? 10 GigE means that the amount of cases when you want to use or have to use CoaXPress or Camera Link are going down and down. That means you need in lesser cases these special interfaces like CoaXPress and Camera Link. So GigE is coming, and of course FireWire is vanishing for, even faster. Of course, machine vision means always I/O capability. Whatever like a digital I/O or any bus system, this is independent if you do 2D or any of the others, thermal or 3D machine vision. What's interesting is if you need I/O, especially for 1D machine vision, these are line scan cameras, and either you have a very stable production process and a stable movement of your parts, then you can run the line scan camera free. This is one of the reasons why my 1D machine vision is not so often used, because the line scan camera generates you one line, and if you want to see an image, you have to add multiple lines after each line after the other to get a 2D image, which you as a human can see. And of course, depending on what the task is, you also need, in many cases, at least more than one line. For example, if you want to make a hole detector in a production unit for foils, either if it's aluminum or steel, you want to see the holes in these metal parts, then you of course, either you say, okay, if I see a gap in one line, but in most cases a gap in a line or multiple gaps in a line is not a hole, maybe whatever it is. Mostly you need, let's see, 10 or 20 lines to get a real view of the 2D representation of this hole, even if it's only a few micrometers. And therefore, you have to connect the camera or the system to an encoder. And of course, you can connect the encoder either to this PLC stuff, or in most cases, the cameras do have a direct encoder input, which many of the 2D cameras also have. In that case, the question is, what do you need for communication for a 1 or 2D system? If you connect the trigger or the encoder directly to the camera, you can use, and that's what we see right now, you can use the standard bus protocols to communicate with the machine or with the rest of the system. In this case, we see, if we are in Europe, we see a lot of people who use Profinet, not so much Profibus nowadays, or Modbus, and some of the other interfaces. And more we see also UPC UA or MQTT as interface system. And of course, many communication, if you have a robot or whatever, and you have connected it to your system, even, and also if you have the camera connected to it, you use in many cases TCP connection is used. Then you don't need these additional really 24-volt hardwired PLC. Of course, RS-232 is still an interface which is used. Everybody named it outdated and nobody wants to use it, but we find a lot of applications from time to time. So finally, we come to these, to the cameras, and of course, there are endless manufacturers. Here is only the overview of supported camera manufacturers from the software. So it means if you have one of these manufacturers, they normally produce all kind of cameras, or 1D cameras, line scan cameras, 2D cameras, area scan cameras in gray and color. Not all, but many also produce 3D cameras or thermal cameras. And the same is valid for hyperspectral cameras. Hyperspectral, there is only a small camera community which does it for the moment. I think it depends only on the availability of the sensors for the moment. But you get from all of these, let's say these 2D sensors with the standard interfaces like MIPI, USB 3, GigE, and of course also the camera link and co-express. So how does it look like? So this is an old USB 2 interface. As I told you, I think it's outdated. USB 3 is nowadays more what's up to date, because it's much faster and more stable than USB 2. And here are only a few examples of these cameras from the different manufacturers. Here we see a FireWire camera with FireWire A, and anyway, it's also B1 or any Geek E cameras. And here you see the camera link interface with different options. So you have 1 or 2 depending on the speed. Of course, as I told you, the next big thing is the CoaXPress. So you get CoaXPress cameras also from many manufacturers. These are so mini coax connectors. It's a coax cable at the end, and it's connected. Depending on the speed, you need 1 or more to meet the speed requirements for the customer. And of course, beside of these CoaXPress cameras, you need always a board in your PC which supports the interface. And of course, if you use only, this is also a special CoaXPress camera, if you use only 2 connectors of these, and that's the majority of all CoaXPress cameras, you could also handle it with the 10 gig E, which means the number of CoaXPress applications will be not so often that you need it, but anyway, it's important to support it. And as I mentioned, there is the MIPI interface. Of course, there are a lot of other manufacturers. This is only from the mainstream, the Raspberry Pi. Now you get it also from many of the main manufacturers like Basler or AVT and some others. You get these interfaces and you can use it as any other camera. And if you can combine it with one of the embedded systems, you have simply also a smart camera or an embedded system, however you name it, because what is a smart camera? The sensor and the processor in one housing. If you compare the Raspberry Pi and the MIPI camera module and try to fit it in a housing of these PC-based smart cameras, it fits anyway inside, so you could make it also based on these components. So this is a rough overview. Here we see also these line scan cameras, these cameras. Of course, the line scan cameras are especially interesting for really high-speed data transfer, not always. So you find many line scan cameras with the CoaXPress or camera link interface, but as I mentioned, with the Gig E and the 10 Gig E, you could also make these line scan solutions based on the standard interface. So yes, this was now a short overview about the hardware. As I mentioned, there are some other cameras I just jump over. If you don't know it, you can take the time to have a look to these other cameras which are also supported, and maybe a short look to the thermal cameras. We saw an example for these 2D evaluation. If you have something which is a develop heat, either process heat or processing heat, then you could use in many cases these thermal cameras from all these different manufacturers, and do the thermal camera evaluation. You get it also as a smart camera, so that you see the contrast which you want to have is exactly what you need for your evaluation. And when a thermal camera is the better solution or so, simply maybe you ask us, we can give you an idea, or if you tell us what application you have, we can give you an idea which combination of camera might help you to solve this task. And here, as you cannot see the difference. This is a hyperspectral camera. So there are not so many sensors. Most of the manufacturers use the same sensor. That's why we support for the moment this camera here. It generates as a resulting output. It's called a cube. This means these are 16 images, and each of the image has a different 2D image of the represented wavelengths. At the end, hyper camera solutions are based on hypercubes, and depending on the task, either you have to calculate between these different wavelengths images a resulting image to operate on it, which means it's always a 2D image. Or if you know, I have a part, I have 2 parts in my production process, or 3, which fits into 3 of these image stacks. Then you can simply select these image stacks and do the 2D evaluation directly on these image stacks. So that's at the end, the hyper spectral image analysis depends on how many different wavelengths resolutions do you have, or your camera can do. Of course, you can do hyper or multispectral image evaluation also based on filters. If you use, for example, a camera where you can change the filters in front of the sensor, you can maybe capture 3 images with 3 different filters. So you have a multispectral image, you have a cube with 3 layers, or you use different lights with different wavelengths, and you look to the reflection of these lights. This is also a multi-spectral image. But at the end, for each of the images, you get a 2D image on which you normally operate with your tools. Sometimes the combination of these images generate the resulting image. This is more, but this is an multi-image combination. It's kind of processing on these images, and therefore I would leave the hardware presentation. I think you saw now a lot about cameras and lights, and maybe let's have a look now to the iVision software and how to operate on these different kind of images and what it helps you, and how you can make solutions for it, because this is the other step of it. And therefore, let's start with the iVision software. I think most of you hopefully had the time to download the software, or maybe attended one of the other webinars which we had, and have now an insight to the basic components of the software. Anyway, for the people who are new, some are, I see. A short intro to the software. Of course, we have here on the right side the tool section, which allows you to operate on all kind of images. In this case, we use, because we are 1D and 2D, or thermal images, which is at the end a gray image. Of course, everybody speaks about thermal, but if we have a real close look to a thermal camera, the thermal camera generates at the end as a 16-bit, but with let's say something between 12 and 14-bit valid data, valid image information. And if you have a close look to it, this represents dark and bright areas of an image, means a gray image. The difference is you get the calibration for these dark and bright areas, so that you can say at the end the brightness level represents a temperature, so that you can say, okay, this is very bright in the spectrum of 14-bit, then it's 180 degrees, and this is not so bright, then it's 80 degrees, or depending on the range you have. So, but from the standpoint of the software, it's a gray image. And if you remember at the beginning, where is the software used? Of course, it's used everywhere, because at the end, either it's a color or a gray image, or a 3D image. That's the major. The 3D image is, for the moment, if it's not a depth image, if it's real point cloud, then it's a difference. But also you could have a look to the point, to the depth, to the 3D image as a depth image, and then it's also a gray image. Point clouds have some advantages. That's why you will see here all these special point cloud tools. But if you look to the only to the gray values, you could use the gray value evaluation tools to operate on it. And if you want to really operate on thermal images, we have these thermal tools inside, which really take care about the temperature or some special behavior of the parts when they are initiated with a temperature. That means people name it lock-in thermal imaging or pulse thermal imaging. At the end, in most cases, you get also a gray image or a sequence, and that's why we see here sequence at the end of the name. You get a sequence of thermal images, thermal gray images, but with some mathematical algorithms, you can then do NDT, non-destructible evaluation. You can, for example, see voids in parts based on these processing of these sequences. And only for these cases you need these special tools. If you want to measure it, if you only want to see, for example, is the heater working, then you can have a look with the camera and use the gray tool and see, yes, I see the heating elements are working because they are bright, then it's okay. If you want to know, do they have 80 degrees or 90 or 100 or whatever, then you need the thermal part of it to get the real value. Or if you want to see, is there a defect in carbon fiber product, then you need these active thermal analysis. Therefore, we have these special tools. For all the other stuff, if you have some OCR, which is based on a thermal writing, you can use also the normal OCR without doing that. So only why we have these special tools, but at the end, it's a gray, a 1D or 2D gray image analysis. 1D means you use only one line and one line after each other. So this is a thermal image. This is a gray image, but no, it is an RGB image, as we can see here. In the camera viewer, you get always the information of the image, and we see here on the value on the bottom side of the value RGB. That means the system has detected a color image. It looks like a gray image, but in reality, it's a color image. So let's open up one of these projects which we have to show, to have a look, a small look to all the different options what we can do or how we can operate on it. And let's start with a very small project. It's called matching. And here we are. We have a gray image. And how can we see it? If you look to the type here, it's gray. And if I walk around this type, we see we see the value of the under the mouse cursor, and you see the gray value. Of course, you could and what I tried to explain you while we discussed it, what we always try to do, or try to do, we should optimize the contrast. This is an optimized contrast. Of course, you don't need this perfect contrast, but it's good if you can organize it based on the pre-processing. Pre-processing means not electronic, it means light and lens. So we see we have a somewhat good illuminated part, but at the end it's not so good illuminated. Of course, we have here a totally bright area, but if you have a look to the edges, we see here it's not bright. So to have an idea how good the illumination is, you can go to the image illumination section, and you simply go to inspector, and if you open up it and you say, okay, I want to have, I want to see how it looks like. So we can have a look to this section here, and now we what I want to do, yes, we simply, this was too small. Now the values are too big. So let's move it over. And on the right side, yeah, we looking here to this area. Now we move over and we see here this lower part. And as you can see, of course, it's bright, but this is a real image because the values are not totally, let's say 255, and then immediately it's 0. The values are changing from a bright level to a not so bright level. And more interestingly, or not more, but interesting is if we go to this area and we go to the bottom area, you will see here we have in the edge areas with 233 and which slowly go to the 300 area. So if you open up the histogram and the pseudo color and we highlight it, we will see it immediately if we reduce so the part, as we can see, is here in this area. But you see here in the center of the part, even the black is not homogeneous. Of course, it's a real image, and more important is you will see at the outline of the image, outer part of the image, you see here it's going to be darker and darker, or not so bright, however we want to name it. This means what we here see is the lens effect. So as wider you, as far you go to the outside area of the lens, the more the light is not so, the intensity goes down to the lens damping effect. So this helps you if you want to adjust the brightness of your image. If you select or improve your lighting, then you should you can activate this, and if you start live image with the camera, you get really the intensity, the colored image, and you can see how to optimize the setting of the iris and iris settings that you have, let's say at the end, something like this. This is anyway a good lighting condition. And so based on this gray image, then you get the input data stream. For the moment, it could be, we don't see it. It could be from a line scan camera. Of course, it couldn't be because it's from a line scan camera. Immediately, we would know we do not have these rectangle situation in the pseudo color area. because if you have a real line scan camera, the illumination could only change from the left and from the right, but never in the edges, because there is no corners of the image, because the image is generated line by line while the part is moving through the part. That's one of the big advantages of the line scan cameras. The other, which really helps, is that you can do a complete shading correction over the line. A shading correction for a camera needs, first of all, a good calibrated basic image and calculation time. But you could do, for example, the shading correction of a line directly while the incoming line, directly through the incoming line. And in many cases, because you try to have a homogeneous image from left to right, it's really important to correct these lens effects. And for a line, you can do it very simple. You can do it also with the FPGA pre-processing, and that, if you remember, for the smart line scan camera, we had this Zynq CPU with an FPGA on board, which can do this homogenization through the line. So if you have a line scan camera with these artifacts from the lens, you could correct these for each incoming line, and you wouldn't see it in the field of view. And it's in the pre-processing phase before the image is in your processing, in your operation. So to have an idea about the quality, you have also these other tools here, which allows you simply to do some quality, to get a quality idea of the image. Of course, finally, if you want to have a fast look to the image and the quality, you can also use the magnifier or the zoom session of the zoom section of the camera viewer, which enables you easily to go through these images. Besides light and lens, of course, you have also the option to do some image improvements simply with the camera parameter settings. So after you have selected the right light and lens and filter, maybe you have also the option to either change the integration time of the camera. And you have this option if you activate the camera settings menu here. Unfortunately, I don't have a connected camera here for the moment, so that I cannot show it to you. There you have the shutter speed, the integration speed. You have also gamma correction. These are, let's say, image processing, first of all, the shutter and gain values have a direct influence on the sensor, which gives you some control to the sensor data. And the gamma correction gives you an option to improve or highlight, or no, not highlight, to change the values based on the gamma curve. This are some things which could be done if you cannot improve or do the light perfectly for the scene. In most cases, you should try it to solve it without these corrections. without these electronic corrections. Electronic corrections are as good as all these filters. Of course, I told you there are a lot of filters, but normally you use the filters only if all the other stuff is not working. The electronic filters, if you have a bad signal, of course you can try to improve the bad signal. If there's no way to make it better with the light, of course, why not trying to do it with the electronic improvement? But in most cases, you should. It's the last thing what you should do. Before I see the time is running like hell for the moment. To have a look, what you can do also. So we have a lot of basic solutions, and if you're interested, maybe if you do some stuff in the beverage industry, if you download this, you can see here some examples for the beverage industry. And also you see here, you're not restricted to one. You can have as many camera viewers and image memories as you want. And you can operate on these. The same is, so we simply try to put for some industries some examples, and in most cases these examples would also show you or give you some inspirations for your tasks. So, for example, if you have these threads, we have a special tool for thread inspection. As you can see here, of course, this is not the best image, but it's all okay. Of course, we have a lot of contrast, but related to these, to the first image we had, we see here, if we activate the pseudo colors, so you see here, this is something what you normally see if you have normal lighting conditions. And you see here the effect of the lens much more. Maybe also, I don't, these are some customers' images, maybe it could also be based on the lighting, but it looks mainly based on the lens effect. But at the end, what's important here is, if we go through this, you see here the part itself is within a few dark gray levels, and we have a big distance to the backlight. In this case, of course, it's a backlight situation. I didn't told this, so that the contrast is at least between, let's say, 10 and 150, which allows to have real stable values. You should always try to have between the part and the background a big gap, so that the algorithms have an option to decide when they find edge or not. All the tools are based on edge detection, of course, for in 2D or gray level differences, contrast, and okay, so for example, we could use this search and measure example, and depending on this, you see here, in this case, we have a real bright one, and then after a while we get better illumination. I remember this. Here we see it, and it works anyway. But if we compare, and we see this in these in the histogram level now, if we compare the values between the gray background and not so bright background, we have a very slight change in the values. This so the more stable, the higher the contrast is, the better is at the end the solution, or the whatever. If you do measuring or whatever, the better the contrast, the better the solution. Here you see with the statistics, it's only to get an idea what is the difference between high contrast and low contrast. If of course in most cases maybe 100 is good, but if you are in the micrometer or also in the hundreds, and it should be very stable to get your CPK, your process qualification. You need a good illumination to make the solution, and therefore we have all for all the demos we made here, we have all these images inside that you see, or also can test what is the difference between contrast and all the others. I really can push you to download the demo version, the iVision demo version, and it works, and all these examples, and maybe you go through these different applications to see what can you do, or how it's possible to make solutions. For example, if you want to detect, is this the right piece on the part, maybe sometimes even a filter could help you, or let's say in this case it's not a filter, it's a filter, it's a Fourier transformation. Maybe you know it from your training sessions at the university. If the right combination, if you select the right combination, you can result in the solution you need. I would say yes. Thank you very much that you took your time and had a look to it. I hope it was interesting for you, and I say thank you. Hope to see you soon. And if you have any questions, especially for the software or whatever, or how to make solutions, simply feel free to call us or write us a mail. And yeah, happy to help you. Thank you very much. Have a nice day, and hope to see you soon.